I want you to imagine, just for a second, the sheer, uh, the mind-boggling amount of physical internet traffic being generated right this very second.
Oh, it's massive.
Right. Like, we aren't just talking about emails or, text messages anymore. I mean, think about millions of people all over the planet, all at once, sitting on couches, on trains, in coffee shops, just swiping through short videos.
Just constantly demanding data.
Exactly. Millions of thumbs flicking upwards, instantly demanding high-definition video delivered perfectly to a tiny screen. And all of that data is traveling through undersea cables, bouncing off satellite relays, routing through massive warehouse-sized server farms, humming with electricity.
Yeah, video traffic basically absolutely dominates the global internet today.
It really does. But what actually happens under the hood when you swipe and, say, a server halfway across the country crashes right as you're trying to watch something?
Well, it's a fascinating paradox, really, because when the system works, it is entirely invisible to you. You just swipe and the video plays.
Right, you don't even think about it.
Exactly. But when a piece of that infrastructure fails, it is an absolute split-second state of emergency for the network. I mean, the code has to scramble to fix the problem before you even notice it happened.
Which is wild.
It is. We just expect the video to play, so we rarely think about the massive kind of tangled plumbing required to make that instant gratification possible.
Yeah, exactly. And that digital plumbing is the entire foundation of today's deep dive. We are looking at a really incredible study published literally today, June 1st, 2026, by a team of researchers at Northwestern University.
It's a great paper.
It really is. The paper is titled Belt and Suspenders, a study of resilience in TikTok's global video delivery.
And honestly, that title perfectly captures what we're going to look at today. In engineering, a belt and suspenders approach implies a system that absolutely cannot afford to fail.
Right.
It basically means you are wearing a belt to hold your pants up and suspenders just in case the belt snaps.
The ultimate backup plan.
Exactly. It's about having a backup for your backup.
So the mission for this deep dive is to take you on a personal tour through those hidden pipes of the modern internet. We really want to map the multi-layered, heavily guarded infrastructure of one of the world's most demanding applications.
Yeah.
And more importantly, we want to decode what its split-second, fallback strategies can teach you about how the internet actually stays afloat under massive pressure.
Right, because if you zoom out, this isn't really just about one app. It's a lens into how the entire digital ecosystem handles stress, hardware failure, and just the incredibly heavy weight of human attention.
Okay, let's unpack this. Before we can really look at what this app does to keep your videos playing, we have to establish why its specific type of traffic is such a unique beast compared to older platforms.
Sure.
And we also need to understand exactly how these researchers managed to map out a closed, proprietary, highly secretive system without having access to the master blueprints,
Yeah, the why really comes down to the fundamental nature of the content itself. If you think about traditional long-form video, say, you sit down on a Friday night to stream a 2-hour movie or a 30-minute show on a major streaming platform.
Right.
The network requests are actually highly predictable.
Because you click once, and then you just sit there.
Exactly. You ask the server for the movie, the system starts sending it to you, and it quietly buffers the next, 5 minutes of the video in the background while you watch the first 5 minutes.
So it's way ahead of you.
Right. If the network hiccups for 3 seconds, you don't even know because your device already downloaded the scene you're currently watching.
Makes sense.
But short-form, swipe-driven video is inherently chaotic. The researchers noted in this study that the average video duration uploaded to the platform is just 42.7 seconds.
Wow. 42.7 seconds. That completely changes the math.
It really does.
I mean, that means every few seconds, millions of devices are screaming at the network for brand new, unbuffered files. It's rapid. It's totally unpredictable because the app has no idea what you'll swipe to next, and the tolerance for waiting is practically zero.
Yeah, if a 2-hour movie buffers for a couple of seconds at the beginning, you wait, right, because you're invested.
Sure, you've got your popcorn.
Right, but if a 30-second video buffers for 2 seconds, you swipe away out of boredom, the network has to be perfectly instantaneous.
Okay, but knowing how secretive these tech giants are, how did the researchers at Northwestern actually figure out how the network is built? mean, it's not like the company just handed over a neat little map of all their server locations.
No, they definitely didn't have internal access. So they had to get really creative. They set up what they call a massive global active measurement campaign.
Okay.
To capture the web traffic, they used automated web clients routed through VPNs and Docker containers, spreading them across 30 different countries to get a true, global perspective.
Wait, pause for a second. Docker containers.
Yeah.
Are we basically talking about a giant automated bot farm here?
Essentially, yes. A Docker container is basically a lightweight standalone package of software that includes everything needed to run an application.
Oh, I see.
So they could spin up hundreds of these tiny automated viewers all over the world very quickly. But they knew that wasn't enough. Most people don't watch short-form video on a web browser.
Right. They watch it on their phones.
Exactly. The mobile app experience is entirely different, so to get the mobile app perspective, they deployed Android emulators. They configured these virtual machines to act exactly like Google Pixel 4 smartphones.
Okay.
And they ran these fake phones in 5 distinct Amazon Web Services cloud regions: Ohio, Oregon, Dublin, Singapore, and Sydney.
Okay, so picture this. They have this army of fake virtual phones and web browsers scattered all over the world, constantly swiping, watching videos, and demanding data.
Yeah.
But how are they actually mapping the network? Like, I read the paper, and they mentioned analyzing things like DNS lookups, HTTP response headers, and server name indication, or SNI. For someone who isn't a network engineer, what are they actually looking at?
Think of every video file sent to your phone as a physical package in the mail. DNS lookups, HTTP headers, and SNI. These are essentially the digital shipping labels.
Okay, so it's kind of like, imagine trying to map out FedEx's entire global logistics network, but you aren't allowed inside their warehouses or offices.
Right.
All you can do is stand on your porch and obsessively look at the barcodes, the return addresses, and the routing numbers on the boxes that actually show up at your front door.
That is a perfect way to visualize it. By analyzing millions of these digital return addresses, they could identify exactly which specific networks were feeding the videos to their devices.
Wow.
But what's fascinating here is how they took it a step further to test the resilience of those networks. There's a technique called failure injection.
Because they needed to see what happens when things break.
Right.
But they couldn't exactly hack into a tech giant's real servers and unplug them, right?
No, that would be highly illegal. So instead of breaking the server, they broke their own connection to it. Yeah, they use local firewalls on their emulated fake phones to intentionally block the IP addresses of the specific video servers they were connected to.
They basically tricked their own phones into thinking a massive internet outage just wiped out the server they were watching a video from.
Precisely. By simulating a sudden localized outage entirely on their end, the main network remains completely unaware anything is wrong.
Right.
This forced the app on the phone to panic, scramble, and reveal its autonomous backup plans in real time. I mean, the app had to figure out how to get the video to play when the primary path just vanished into thin air.
That is genuinely brilliant detective work. They literally forced the app to show its hand.
They really did.
But before we get into the chaos of those simulated outages, let's look at what the normal, steady-state delivery looks like. How does a video actually reach your phone on a sunny day when everything is working perfectly?
Well, the baseline for this kind of global scale is always a multi-CDN strategy. They don't rely on just one single provider.
Okay, before we get too deep into the alphabet soup here, for anyone who doesn't build websites for a living, what is a CDN functionally? Like, why do we need content delivery networks?
Think of it like this. If a company makes a popular shoe in a factory in New York, and someone in Los Angeles wants to buy it, shipping it from New York every single time takes too long and costs way too much.
Sure.
So the company puts a local retail store right in Los Angeles and stocks it with the most popular shoes. A CDN does exactly that, but for data. It's a massive network of servers strategically placed all over the globe, designed to store or cache heavy files like videos as physically close to the user as possible.
So it's basically a local digital convenience store. That way my phone doesn't have to drive all the way to a central warehouse halfway across the world just to load a 15-second dancing video.
Exactly. And the study found that TikTok's strategy for using these CDNs is highly regional, and it depends heavily on whether you are using a web browser or the mobile app.
Okay, let's start with the web traffic. What did they find there?
They found that web traffic heavily relies on a massive third-party CDN giant called Akamai on a global scale.
Okay.
But in certain places, this infrastructure is basically merged directly with the local internet. For instance, in Peru, through a provider called Telefonica, or in Finland with a provider called Aurelion, Akamai servers are physically embedded directly inside the local internet service providers.
Wait, why would a local internet provider in Peru let another massive global tech company install their physical hardware directly inside their local network hub?
It's a strategy known as an accelerated network partner, or AANP. It's totally mutually beneficial.
How so?
Well, for the video app, the data is hosted right inside the user's neighborhood network, meaning practically zero delay. And for the local internet provider, it saves them an enormous amount of money.
Because they aren't fetching the data from far away.
Right. If the video is already sitting inside their own building, they don't have to pay expensive transit costs to pull that heavy video traffic across the global internet backbone every time a customer wants to watch it. Fastly acts as a global secondary backup there.
That makes a lot of sense, essentially. So that's the web. But when you switch to the mobile app, which is where the vast majority of this traffic actually lives, things get wild.
Very wild and highly fragmented. In the Asia-Pacific and Oceania regions, specifically looking at their test nodes in Singapore and Sydney, the mobile app operates as a total monolith. Meaning the researchers found that roughly 99% of the traffic there is served by the company's own in-house CDN called ByteDance. They own and control the entire pipe from start to finish.
Okay. But in the U.S., specifically their test regions in Ohio and Oregon, it uses this incredible chunking strategy.
Yeah, it's
They
fascinating.
literally slice the video up. When you open a video on your phone in the U.S., the very first segment, the startup chunk, is overwhelmingly served by that third-party giant, Akamai.
Over 80% of the time, yeah.
But if you keep watching and don't swipe away, the subsequent chunks of that exact same video are suddenly handed off midstream to ByteDance, or another CDN called Fastly.
And just to add to the complexity, over in Dublin, it's a completely different story. The mobile traffic there is highly fragmented from the start, split among CDN 77, Fastly, Akamai, and G-Core.
Okay, stop right there. I'm genuinely confused by this U.S. strategy.
Yeah.
Here's where it gets really interesting. If the parent company has this massive proprietary network in-house, and they use it to handle 99% of the traffic effortlessly in places like Singapore, why divide the chunks at all? Why not just use their in-house ByteDance CDN for everything in the U.S. like they do in Singapore? That sounds like burning money to pay a middleman when you literally own the pipes.
It sounds totally counterintuitive until you remember the psychology of the swipe and that unforgiving 42.7-second window. The startup latency is everything.
Because it buffers, you are gone. Exactly. Akamai is an older legacy giant. They have spent decades building a phenomenally dense, deeply embedded physical footprint across the vast geography of the United States.
Oh, I see.
The researchers observed that Akamai achieves a stunning 94.6% cache hit rate for those crucial first milliseconds.
Ah, so they basically use Akamai as the ultimate hook. They know Akamai servers are sitting right down the street from the user, so they pay them to get the video playing instantly.
Precisely. It's a calculated expense. Once you're hooked and watching the video, they've bought themselves a few seconds of buffer time.
Right.
Then, and only then, they quietly offload the rest of the heavy video file to other networks like their own in-house ByteDance servers. Those in-house servers might be way more cost-effective for bulk data transfer, even if they're located a little further away physically than Akamai.
Okay, that is a staggering level of real-time financial and technical choreography just for a 30-second trend.
It really is. But all of this chunking and seamless handoff only works beautifully when the internet is sunny. Let's get back to the trap the researchers set. What happens when they intentionally break the connection? What is the app's actual survival instinct?
This is where the researchers mapped out a really fascinating taxonomy of survival. They noticed that the app basically has 4 different distinct fallback behaviors when a connection suddenly dies, and it varies heavily by region.
Okay, what's the first one?
The most straightforward one they observed, mostly in places like the Netherlands and Ireland, is what you'd probably do if you walked up to a store and the sign said closed. You just walk down the street to the next open store.
They call this linear fallback in the paper.
Yes. The app's code simply abandons the failed CDN, moves down its pre-programmed list to the next backup provider, and doesn't look back. It provides a very fast, predictable delay.
That seems logical, but does it always just give up and move on that cleanly?
Not always. In the US and Canada, they saw a much more stubborn behavior called a loop retry.
Loop retry.
Yeah. In a loop retry, the app switches to a backup, say moving from Akamai over to Fastly, but it keeps checking over its shoulder. It constantly pauses to see if the primary CDN is back online yet.
That sounds incredibly chaotic. Doesn't that cause the video to stutter more?
It does. It creates higher delay variance, meaning the recovery time for the user is way less predictable because the app is constantly second-guessing its connection.
Why would the app purposely do something that makes the viewing experience worse?
Well, if we connect this to the bigger picture, you have to remember the business and engineering trade-offs behind these choices.
Okay.
Take the concept of cache locality. If the app switches to a totally new network, that new network might not have the video you want saved locally yet. It has to go fetch it from a central server, which takes time.
Right.
Returning to the primary CDN preserves that cache locality, and perhaps more importantly, these companies have massive volume-based pricing contracts with their primary providers.
So it's about the money.
Largely, yes. They want to get that traffic back onto the preferred, cheaper pipe. The absolute second it's clear, even if it causes a tiny momentary stutter for the user.
It's an economic decision written into the code. What if the app doesn't want to switch providers at all? Do they ever just try to fix it internally?
They do. In places like Korea and Finland, they observed hierarchical fallback.
What's that?
This happens when the app exhausts multiple different servers or edge nodes entirely within the same CDN before finally giving up and switching to a totally different provider. It's a very thorough, step-by-step exhaustion of local options.
And what was the fourth flavor?
Sometimes they execute an intra-CDN fallback. This is the quietest failure of all. The app stays with the exact same provider, but just quickly connects to a different server rack, basically in the same building. It absorbs the failure so fast you barely notice a thing.
You think about the last time you were lying in bed late at night doom scrolling, and a video just visual stuttered for half a second before continuing perfectly, versus a completely ruined, frozen feed.
Yeah.
You were physically feeling the difference between a clean intra-CDN reroute and a messy loop retry. Millions of lines of code were scrambling in real time, right there in your hand to save your viewing experience.
And doing it all in milliseconds.
Yeah.
But here's the critical pivot in the study. Everything we've talked about so far, the chunking, the loop retries, this is all for video on demand, regular scrolling of pre-recorded videos.
Right.
In that scenario, the app actually has the luxury of a roughly 10-second buffer to figure out these fallbacks in the background while you watch the start of the video.
But live streaming is a completely different, totally unforgiving tightrope, isn't it?
Oh, live streaming changes every single rule. Because there is no future video to buffer, it is happening right now.
Yeah.
For live video, the study found that TikTok largely abandons those massive third-party CDNs. Globally, roughly 75% of web live sessions and 61% of mobile live sessions are pushed directly through ByteDance's own proprietary infrastructure.
Wait, why abandon the big players like Akamai and Fastly? We just established how great they are at instant delivery.
Because third-party CDNs are historically built around caching. They excel at storing static files like a pre-recorded video or an image close to the user.
Right.
But live streaming demands real-time ingestion. You have to take a video from a creator's phone in Brazil, process it, and push it to a viewer in Japan in less than a second. Standard caching architectures really struggle with that continuous, unforgiving flow of real-time data.
But that means when hardware fails during a live stream, things get really ugly, right? Because
Yeah.
you don't have that 10-second buffer to hide the scramble.
They get incredibly ugly. The researchers found that when they injected failures during live streams, 46.5% of web fallback attempts instantly timed out.
Almost half.
Yep, the connection drops and the stream just dies. There is literally no time to hunt for a backup.
So it feels like video on demand is basically a delayed train. It's really annoying. The train snows on the tracks. Maybe the lights flicker, but the passengers eventually arrive at the station.
Yeah.
Live streaming is a relay race. If you drop the baton, the race is over instantly, no matter how many backup runners you have sitting on the sidelines in tracksuits.
That is the perfect analogy. And the data from the study proves it, highlighting a concept they call brittle diversity.
Brittle diversity.
Yeah. They looked closely at the Asia-Pacific regions, like Australia. Now, in Australia, the app uses a mix of ByteDance, G-Core, CDN77, and Akamai for live video. On paper, to a network engineer, that looks incredibly diverse and robust. You have 4 entirely different corporate networks sharing the load.
You have 3 backup runners on the sidelines.
Exactly. But when the researchers actively blocked the primary provider in Australia, an astonishing 81% of live streams simply timed out.
81%.
Yes. And in Singapore, which theoretically relies on a dual setup of ByteDance and CDN77, it was a 43.8% timeout rate. Having all those backups on paper didn't help because the software simply couldn't swap them in fast enough before the real-time stream collapsed.
So having 4 backups in Australia actually led to an 81% failure rate. That completely shatters the idea that more backups equals more safety.
It really does.
But earlier you said the U.S. relies on this complex chunking and third-party setup. What happened when they simulated a live stream failure in the U.S.?
Huh.
Did it collapse too?
Surprisingly, no. The US operates differently. It uses a dual primary setup for live streaming, splitting the load cleanly and equally between CDN 77 and ByteDance.
Okay.
The researchers found that in the US, blocking either provider redirected traffic cleanly and instantly to the other with almost negligible timeouts.
So they actually figured out how to hand off the baton in the U.S. without dropping it.
They did, and this raises an important question that goes way beyond just social media. It forces us to challenge our basic assumptions about redundancy in tech. Well, for years, we've thought that simply having multiple providers' diversity equals safety. But this study conclusively shows that for highly sensitive, real-time applications, having multiple providers on paper does absolutely nothing if the failover pathways aren't tightly and operationally integrated.
Right.
It's not about how many backups you have, it's about how perfectly synchronized the handoff is.
So what does this all mean when we put the pieces together? We've seen that the delivery strategies keeping your app running aren't static. They change dynamically based on what country you're sitting in, the exact second of the video chunk you're currently watching, and whether that video was recorded yesterday or is broadcasting live right now.
It is a phenomenal, highly adaptive machine. The sheer engineering required to maintain the illusion of instantaneous, perfect video across a chaotic global network is staggering.
It really is. And that's exactly what we want you to take away from this.
Yep.
The next time a video loads instantly or stalls for a second while you're swiping, you now know about the invisible, highly choreographed CDN ballet happening in milliseconds right behind your screen.
Yeah.
It's not just internet magic. It's linear fallbacks, local internet embeddings, and calculated startup junks working furiously to keep you entertained.
And occasionally a very quiet intra-CDN reroute saving the day without you ever noticing.
Exactly. But I want to leave you with a final, slightly more provocative thought to mull over or explore on your own. The researchers proved here that for real-time data, having a diverse list of backup providers often results in brittle diversity.
Right.
It looks incredibly safe on a spreadsheet in a boardroom, but it shatters under pressure when a single millisecond actually matters. Now think beyond video apps. As our society moves toward relying on the internet for highly critical, real-time tasks, think about remote robotic surgery or fully autonomous self-driving traffic grids in major cities. Are we actually building a resilient infrastructure?
Yeah, that's the big question.
Or are we just relying on the comforting, dangerous illusion of brittle diversity? Keep thinking about that sheer mind-boggling volume of traffic, and we'll catch you on the next deep dive.